Hello everyone, we are continuing on the mechanical properties of materials, and in this video we will be looking at the elastic constants for isotropic and anisotropic materials. And in our last video we have seen modulus of elasticity, which is a characteristic property of elastic materials. And also we have seen the concept of isotropy and anisotropy. And we have seen that if we were to test wood parallel to the fibers versus if you were to test the same wood perpendicular to the fibers, we can get two different modulus of elasticity, two different material behavior, in other words, and that makes wood as an anisotropic material. Now, in this lecture, we will be looking at another characteristic property of an elastic material that will be termed as nu. For that, we will be again looking at the same type of loading of a rod that has a diameter of d0 and a length of L0, let's say. And again, we are pulling it in longitudinally, so uniaxial tension test we are subjecting this rod. If you were to subject that rod to these tensile stresses, it will deform, and the deformed shape will look like that, and the length of that will be like final length LF. And as you can see, the along the transverse direction, so perpendicular to the load axis, as you can see, there is some sort of a shortening. Therefore, it shrinks in transverse direction. And if we were to put these x, y, z axes like that, and if we are looking at, let's say, from the top cross section, as you can see, there is some shortening, and from the side, as you can see, there is some longitudinal elongation and transverse contraction. So this longitudinal elongation we can term as delta, and we can term the shortening in the transverse direction is small delta. And having learned what strain is, the longitudinal strain can be obtained by dividing the deformation delta to the original length L0, or final length minus original length divided by L0. So this is the longitudinal strain. And we can also have another strain transverse to the load application, and that is again defined the same way, delta, so the deformation transverse, divided by d0, so the original cross-sectional diameter. And again, we can write it final diameter minus original diameter divided by original diameter. If we were to label these strain values with this XYZ coordinate system, this will be termed as epsilon ZZ, and transverse direction strains will be considered as epsilon XX or epsilon YY. So along the x-axis or along the y-axis, they will be the same. And remember, for an isotropic material, we can say that these strains are equal to each other. Well, the reason why we observe an elongation longitudinally and a contraction transverse is, again, a material property tells us that. And that is known as Poisson's ratio, and it is defined as the ratio of transverse contraction strain, transverse strain, to longitudinal extension strain in the direction of stretching force. So if you were to plot this epsilon L and epsilon T, longitudinal versus transverse axes, so longitudinal and transverse axes, see the Poisson's ratio is defined as the slope. Note that there is a minus sign over here. Epsilon transverse strain divided by longitudinal strain. We will come back to this minus sign in a little bit, but let's look at this dimension. As you can see, strain divided by strain is dimensionless. So Poisson's ratio does not have any dimension. So in an isotropic material, the theoretically admissible range of Poisson's ratio is that it can go as far as -1 and it can go as high as 0.5. And this limit 0.5, we will come back in our next lecture. But virtually all common materials undergo transverse contraction upon stretching in one direction and exhibit transverse expansion upon compression. And that's the reason why we have this minus actually. So if transverse strain is minus, longitudinal strain is positive, or vice versa. If this is positive, this one is negative, making Poisson's ratio most of the time greater than 0. So practically the range of Poisson's ratio is restricted to 0 to 0.5 for most, I called it, non-exotic engineering material. For instance, like metals, they do have Poisson's ratio about 0.33. Concrete, it's about 0.20. Polymers, about 0.40. Some foams or from engineered materials can have a Poisson's ratio less than 0, meaning that if you are pulling a material in one direction, it is expanding in the other direction. Okay, but that's, as I said, for that can be considered as a non-exotic. That those are like exotic materials, I should have said. So the elastic constants, the modulus of elasticity that we have learned as the slope between stress to strain, and the Poisson's ratio, which is transverse strain divided by longitudinal strain. What do they tell us? What's their significance? I will show them in, again, a uniaxial tension test. We have this rod, we are pulling it, let's say. If we know these two material properties, we can calculate the deformations of this bar. What are the deformations? The elongation in length, how long it will get, or the reduction in diameter, how much it will shorten in the transverse direction. We can calculate that. Or the same problem, not in tension but in compression this time. Knowing these modulus of elasticity and Poisson's ratio, we can calculate the shortening in length of this rod or the elongation in diameter for this rod. So remember, for small deformations, normal stresses cause either elongation or shortening. So we have normal stresses over here, either tension or compression, and they will cause elongation and shortening. So along the load, we can have shortening, and transverse, we can have elongation. And we have learned for small deformations again, shear stresses cause distortion type of deformations. So we have covered the top part now. How about the other one? So what happens when a material is subjected to a pure shearing stress? Well, where do we see such cases? We have seen that in the case of a shearing of a rivet, we can have a pure shear stress that can be calculated like that. Or in the case of a torsion on a rod, that has a diameter of r and a thickness of t, let's say, the pure shearing stress will be the torsion divided by 2p RT. And we have seen the whenever we apply these shearing stresses, we can calculate the amount of shearing strain gamma as tangent theta. And remember, shear strain is unitless. Well, what dictates gamma whenever we apply tau is given by the modulus of rigidity, or we call shear modulus. So, in other words, the slope of shear stress and shearing strain gives us the modulus of rigidity, or the shear modulus. So it's a characteristic material property. And shear modulus is defined as the slope of the shear stress shear strain plot, often represented as G, and its unit is gigapascals. Now, Hooke's law. For elastic materials, stress is linearly proportional to strain and is independent of time. So this was given by Hooke, and we have seen this type of a behavior. Stress is proportional to strain and is independent of time. And so this E is, we learned, as modulus of elasticity, or we termed this as an elastic constant. So this simple state of stress can be generalized as a generalized Hooke's law. So in a three-dimensional setting of linear elasticity, that one-dimensional Hooke's law can be generalized to the tensorial constitutive relation of an anisotropic material. So one-dimensional is extended to three-dimensional. So we have these matrices now. So according to the generalized Hooke's law, the stress tensor is related to the strain tensor, and what we have over here is a fourth order elasticity tensor that can be expressed mathematically like that. And remember, in linear elasticity, we are always considering small deformations, small strains. So here is the general case. We have these stress components, 9 stress components that are assembled in a matrix form, and we have this 9 against strain components that are assembled in matrix form. And if you remember, the diagonals are normal stresses, and over here the diagonal is normal strains. And the off diagonals are known as shear stress, and over here they are called shear strains. And we have also seen that sigma 1, 2 is equal to sigma 2, 1, or epsilon 1, 2 is equal to epsilon 2, 1, and that tells us that the stress tensor is symmetric and the strain tensor is symmetric. So what does this tell us, or what does it help us? And before going into that, I have to mention that normal stresses, we often show them as sigma. Shear stresses, we often show them as tau. And normal strains is shown in epsilon. Shear strains is shown as gamma. And during our description of shear strain, I made some simplifications in order not to confuse you. But in fact, the strain can have two components, epsilon 1, 2 and epsilon 2, 1. I combined them into one, and I added these two to show you only one shearing strain. Now, this symmetry, we can utilize it, and we can write this generalized Hooke's law in a different matrix form, and which is referred to as Voigt notation. So this is the elasticity tensor, This is the stress tensor, but look at over here. It's not in a matrix form, it's rather a vector form, and this is the strain components, again represented in a vector form. And stresses are proportional to strains through some elastic constants. And this matrix basically termed as elastic constants of a material, and the most general case for an anisotropic material. And remember, these are normal stresses, these are shear stresses, and come back here, these are normal strains, and gammas show us shear strains. So let's look at this now. Well, it can be shown that the elasticity tensor is also symmetric, and that reduces the number of elastic constants. If you count over here, you will end up with 21. So that shows us that the number of elastic constants reduces to 21 for a general anisotropic material without any symmetry properties. Furthermore, for an isotropic material, the number of independent elastic constants reduces to only 2. So there are, if you know 2 material properties, you can characterize an isotropic material behavior. And you have seen, in fact, those 2 material properties. So again, if you come back to here, for small deformations and strains, we know that our normal stresses cause normal strains, shear stresses cause shear strains. That makes us these diagonals as 0. And these 2 diagonals are related to E and nu, which are the material characteristic material properties. And this diagonal is related to G, the modulus of rigidity or shear modulus. In fact, in a little bit, in our next video, we will be seeing that the shear modulus can be expressed in terms of modulus of elasticity and the Poisson's ratio. So, for a generalized Hooke's law of an isotropic material, it will lead us to the compliance relations, which are now strains to stresses. We can write them, in other words, like the normal strains can be written. So normal strains can be written as a function of the stress components. So strains are related to these stress components. So the normal stresses, of course, these are. And what are they related to? The modulus of elasticity and Poisson's ratio. When it comes, so the other normal strains can also be written in terms of normal stresses. When it comes to shear strains, see, gamma 1, 2 can be expressed in terms of tau 1, 2, shearing stress, and they are related with shear modulus, G. So for an isotropic material, we have E, nu, and G, and soon we will learn that we can express this shear modulus in terms of these 2. So the generalized Hooke's law can be expressed in terms of a compliance tensor, which is the inverse of the elasticity tensor. So therefore, we can now relate strains to stresses. So strains are related to the stress through what's called a compliance tensor. So if we know this, if we know the material properties E and nu, then we can calculate the strains knowing these stress components. So that's what the compliance tensor tells us. Again, remember, normal strains, shear strains, and normal stresses, shear stresses. So how can we use this? Let me show in an example. Again, we have a rod, let's say and we are pulling this rod in the x1 direction. So this is x1. Oh, there you go. x1 direction, x2 direction, x3 direction. So if we take an infinitesimal volume element over here, see, we have only sigma 1, 1 component. All the other stress components are 0. So sigma 1, 1. And knowing the material property of this rod, let's say, and knowing the compliance tensor, and having calculated sigma 1, 1, the rest are 0. Now we can calculate all the strain components of that rod. So that concludes for this video. In our next video, we will be looking at the elastic constants of isotropic materials and their relations.